Hello, this is a new series on computer-aided engineering. So here in this series, I'm going to have various sessions on different softwares which are used for engineering design, right? And then this is in association with number of colleges that I've worked in the past and currently I'm working with, and the companies with whom I have worked with. Okay, so without wasting much time, I'm gonna get started with the first software, which is Advanced Design System from Keysight, right? And this software is very versatile. So I am going to try to cover all the topics in one session. But then, if there are some advanced topics, I might do another session. So here, what I'm going to do is I am going to use two presentations which I have done in the past as the base for explaining things, and I am going to do some writing over here, and then I'm going to run the software and do the exercises in front of you so that you can follow along, and you can pause the video, and you can catch up with if you are left behind. So that's what we are going to do. Okay, so let's get started with the first presentation over here. Here, I am going to walk through few slides here. Okay, so this advanced design system is from Keysight. It has a very glorious history of around 22 years, which I know of, and I started working with ADS in year 1999 when it was a alpha version, and before that I used to work with the software called MDS, and then it grew into something called ADS. Right, at that time it was a HP product, and we didn't even have a manuals for this, so we had to figure out all the buttons and stuff like that. And so beyond that, okay, this software uh, was developed, has matured over many years, right? So initially in 2003, HP spin off the 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 part of the company, uh, and that became Agilent. And Agilent developed ADS and other EDA tools, right? And Agilent was there for almost 10 years till to 2013, where again Agilent spin off the EDA portion from its other streams, like biomedical and chemistry related stuff. So that portion is still Agilent. Now this is now called Keysight, and what comes under Keysight is the CDA tools and measurement equipments, right? So there have been a number of changes in ADS, right? And these changes, you know, uh, over different revisions have resulted in a very versatile software called Advanced Design System, right? So my name is Anurag Nigam, and you can read my LinkedIn profile if you wanted to know where I worked and what do I do and stuff like that. So let's get started. Okay, uh, ADS stands for Advanced Design System. It's used for high frequency and high speed designs, and it can also be used for packaging, right, or for EM simulation, stuff like that, right? So this tool, okay, can be used for a number of disciplines. Like it can be used for CMOS design, it can be used for RF design, it can be used for thermal analysis and design, it can be used for electromagnetic simulation, it can be used for analog circuit design, it can be used for digital circuit design, right? And then you earlier, it used to be running on a single core or two core. Now it can run on multiple cores, so basically speed is enhanced, right? A lot of research has gone into the GUI, reducing the number of clicks and stuff like that, right? So that has gone into that. Then the unique feature of this tool is the user interface. It's very user friendly compared to a software tool like Cadence. Now, but people who are used to Cadence would say Cadence is more user friendly, but according to me, it's much easier to understand the flow in ADS compared to Cadence. So this software tool, right, has always been expanding. Now there are four portions to this presentation. So where I call ADS umbrella means I'm going to talk about various simulators in the tool, and I'm going to also talk about various components of ADS, right? And I'm not going to talk about digital design, analog design, or RF design because they are dealt with in separate playlists, right? So ADS is capable of doing all kinds of designs. Okay, so let's get started with ADS. So now here I am going to depart from, okay, so I'm going to depart from this presentation into a different presentation, and I'll come back to this later on. Right, so this is over here, and sorry. Okay, so here I'm going to give you a first overview of ADS, and then we will do a chapter wise, right? So we have already seen that ADS is a very versatile software, right? Now here the methodology which I'm going to follow is I'm going to give you a tutorial explaining concepts, methodology, and providing overview and discussing the flow. And next thing we are going to do hands-on exercises, applying the concepts which you have learned, methodology which we have established, and then we are going to basically infer from that what is our learning, and we are going to validate some assumptions, right? So this is the flow, which is an integrated flow that I'm going to follow first with the tutorial and concepts and methodology, followed with a hands-on exercise, right? So let's look at the overview of ADS. Okay, so ADS basically a lot of things may be changing under the hood, but the UI is more or less the same, and this is for a purpose that people don't have to have a big learning curve whenever there is a change in UI, and you place things at different places and change the buttons and menus and things like that. So for that reason, the UI hasn't changed much as far as I remember, from ADS 2005 to currently ADS 2021, 22 maybe. Things have more or less remained the same. So as soon as you launch ADS, there is going to be a main window, and this main window more or less is the same, right? And the versions may change, the captions may change, right? But the window remains the same. Right, so there are various components of ADS, right? First thing is we are going to have design resources. So basically everything sits inside a single hood. So these design resources are going to be the built-in libraries of components, like resistors, inductors, capacitors, and stuff like that. Then these are more or less ideal or models which you can use in your design. Then you have got third-party libraries, which are some of them are available, and I'll show you how to use them. But a lot of them, if you are working on with a certain foundry, you would have to sign up with them, NDA, and then you can get access to their PDK, or what is called process design kits. So these libraries are third-party libraries. Also, the package components, for example, transistors, surface mount resistors, capacitors, inductors. Okay, there used to be, okay, these used to be available in ADS, but now this has been now done by a company called Modeletics, and you can sign up with them and you can purchase from them the libraries and stuff like that, right? So these are the third-party libraries. Then it also allows you to import the design from other tools, right? So for example, I can get a portion of a design which is in a different uh, software from same Keysight, like for example EMPro, and then I can import it in the layout in ADS, right? So I can have an import interface to different tools. Then the other design resources which are to assist a designer, these are called design guides. And as far as I remember, it was 2004 and 5 when we started working on design guides. So I used to work with IBM, and Keysight, earlier called Agilent, was consulting, on design of these design guides. So these are various design resources. Apart from design resources, you should have design tools. Like for example, you should be able to do schematic entry, you should be able to do layout entry and stuff like that, right? So these are design entry tools, right? There is a way to interface MATLAB, also to interface your VHDL and Verilog stuff. So that's another way of design entry. The third thing is going to be the visualization tool. So once you have done the simulations, right, you take the results and you should be able to visualize the results in so these are verification tools, sorry. So here visualization tool I'll talk later. Verification tools, we are going to talk about desktop LVS and DRC. So let's say if you have a PDK from a third party, let's say some fab, let's say IHP, then it provides you ability to do layout versus schematic. So that you can make sure that your layout and schematic are in correspondence, and there is a link between layout schematic which shows up, like when you place components in schematic, the changes are aware to the layout, or if you place components in layout, then the connectivity is there with the schematic. So layout versus schematic is available. Then design rule check. So there are design rule check files for third party libraries. So for example IHP, you will be able to do a DRC and would be able to figure out if there are any design rule violations, right? Now mostly this tool has been earlier used for millimeter wave or microwave designs, right? Microwave integrated circuit or millimeter wave integrated circuit, or monolithic microwave integrated circuit or millimeter wave circuit. Now this there is nothing which stops it from being used for CMOS design flow also. So for analog mixed signal also you can use that, and there are numerous fabs which also support post post layout verification and from ADS itself. For example, ISP would allow you to do LVS DRC. Tower Jazz would allow you to do LVS DRC from ADS itself. So these are the verification tools. The other components are simulation tools. Now this is the main engine, right? Here you can do circuit simulations, right? So in under circuit simulators there are different simulators, like for example you can do AC/DC analysis, right? You can do S parameter or small signal or linear analysis. You can do a large signal or a transient analysis like in time domain. You can also do this in frequency domain, like harmonic balance, which is basically developed from what is called Volterra series technique. Harmonic balance you can do, and then you can do a time stepped harmonic balance, which is called envelope simulation. Then there are certain modeling tools, like you can do X parameter modeling and simulation, right? So these are some of the circuit simulator related uh, tools are there. Then there are simulation tools, like for example you can do a method of moment, right, which is a 2.5D. So even your metals can have certain thicknesses, right? But the 3D entry tool is not there. It is a 2D entry tool. So you have a Z profile, but then all your drawings are on the different layers of metals, right? So you can do a planar design very easily in this 2D entry tool, much easier than what you can do in 3D entry tools, right? And then you will be able to export this also to 3D, full 3D entry tool, like for example EMPro. So you can do your designs, layouts in ADS, and you will be able to take them with the click of a button to EMPro. So that you can do EM simulation. So method of moment is the classical simulator which has been there since the inception of ADS. Apart from that, there is FDTD and FEM simulator also, right? So you will be able to do a FEM simulation here. FDTD is in a separate tool like EMPro, but not a part of ADS, but FEM is. So you can do a finite element analysis also, but still the entry tool is going to be 2D, and then the Z profile is provided as a substrate definition. So this is with EM simulations. Then you can do DSP simulations. So there is a component which is called Ptolemy, right? And in Ptolemy you should be able to do digital baseband. So you will be able to do timed as well as non-timed, like based on tokens, like so you can do that in Ptolemy. So Ptolemy allows you to do DSP simulations also. There is a big library of various components for various mobile communication systems, like 1G, 2G, and 3G, and 4G, and up to 5G. Then there would be a lot of baseband design, which would be for, let's say, digital TV, or let's say LAN standards or WAN standards, like Wi-Fi, WiMAX, 802.11, ABG, AC, AD, and stuff like that, right? So you do not have to do everything from scratch. And one more important feature is that all these libraries are IEEE compliant, right? So basically you know that you are working with something which is a industry standard, right? So that is your DSP simulations. So simulation tools are there in this ADS. Then there are visualization tools, which earlier I mentioned briefly. Visualization tools, mainly the data display window, right? Here you'll be able to do rectangular plots, you'll be able to do Smith chart, polar plots, you'll be able to visualize in 3D the antenna pattern, radiation patterns and stuff like that. You will be able to visualize surface currents in metals. You will be able to do so there is a 3D EM preview. So basically once you have done a layout, you will be able to see your design in 3D. And in 3D, the design is more explanatory, in the sense that you can catch your mistakes more easily in 3D simulation, in 3D visualization, sorry. And one of the important features of that is the connectivity, right? The physical connectivity. So if you click a certain metal, it will just highlight all the metals which are connected to that metal. So that way there is a less chances of some open circuits or short circuits in the design, right? So this is there in visualization tools. Then you will be able to do product design, complete product design. So basically the flow goes like this: you first do the prototype, and then in your prototype you can look at the sensitivity of various components on the design performance. Then you can also look at you can also center your designs, so that the component variations do not cause a lot of variations in performance. Then you will be able to do yield analysis, right? Monte Carlo simulation, stuff like that. Then you will also be able to do design of experiments, right? So that's I'm going to cover later on various mimic design of experiments, right? So this you can do. Then you can export your layouts to the fab. So number of fabs are there which allow a tape out from ADS itself, right? You do not have to do layout in Cadence. So layout export is there. Then the final thing is and this is optimizers. Right now I cover optimizers not to great extent, because I'm not so fond of optimizers, right? This is like, if you start using optimizers early in your design career, then you will spoil yourself, right? So that's what I believe. Okay, so these are the components of ADS. Now getting started. Okay, so here I am going to take over as hands-on, right? So any project in ADS is called a workspace, like any software, like for example Visual Studio, right? Your project or solution is called a workspace. And what's there inside a workspace? Everything, actually. Okay, you have support of the design resources, like third party libraries, inbuilt libraries and stuff like that. Okay, then you have simulators, right, to do the circuit simulation, simulation, layouts and stuff like that. Then you will be able to do visualization, like in data display window. You can display your simulation results and then analyze it. You can write equations to do a post processing on these simulations, right? And then you can visualize them, right? So these visualization tools are available. Then you have got optimizers for optimizing your design, centering your design, improving the yield and stuff like that. And then you can finally tape out from ADS. So the main window has remained the same. So getting started with ADS, right? So this window is there in current version also, and it provides you a single click access to all the workspace management, right? Also access to tutorials and online resources for learning and stuff like that. So all this available from this window, and this window appears anytime you close the project, right? So that you can always come back to this window to launch a new project or new workspace. Okay, so this is the main window, and you can open a workspace or create a new workspace. There are buttons for this, or there are menus. And then there are three tabs which you can see: file view, folder view, library view. The folder view is by default what's going to be open. So here what you see here is the folder view, right? And this is the file view. So basically says what all files are available in the current working directory. And folder view is related to your project, and library view is basically categorizing all what is in your workspace into various categories, like for example substrates, uh, design files or data display files. You have categorized this in a library view, right? So the key is you can reference to other libraries. Okay, in if you want to reuse the design from a different library, you will be able to do that. You will be able to copy it. And then you can also so every project or workspace which you open will have its own local library. So all the components which you design will be available in that local library, right? So you can reference from other libraries to design reuse, and you can do designs in your library. So that's how it works here. Okay, now this library is more like a open source XML based results and stuff like that, XML based storage, and that is done basically to share designs between various tools which are with the company Keysight. Like various tools are going to be EMPro, uh, probably Genesys, right, and SystemVue and stuff like that. So that's how the storage is. Okay, so when you start, there is going to be a wizard. So I'm going to follow the wizard. Okay, so once you follow the wizard, now this wizard has gone through changes. Earlier it used to be more elaborate, and now it is like two dialog box based, two dialog box wizard, right? So it's like you do not have to click a lot. Okay, so basically you provide a workspace a name, and then underscore work, WRK, is basically what tells ADS that this is a ADS project workspace. If you shouldn't remove underscore WRK, and whatever you want to give name, it should not have white space characters other than underscore, and should not start with a number or a white space character, or any special character, right? Like dollar sign or hash. It should not. And it should not have spaces, because it may work with the spaces, but at some points it may not work. It may break. Again, then you can attach or reference to certain libraries, right? Add the references to libraries, and then the workspace has its own library which you can name, right? So this is what we are going to do to create workspace. Now workspace basically also has not only the circuit designs but also the layout. So here you can fix the resolution of layout at the start itself. So once we do that, you'll be able to do that. So what do you mean by the layout resolution? That's the minimum size grid which is going to be used for processing, for various processes. So that's what you draw on, and if you are off grid, your fab may not accept that layout. Now there is a neat option here that if you want to edit something which is a part of PDK, right, you can copy the library instead of referencing it. For example, let's say if you have a metal stack up and you want to add two more layers for the board underneath, so you can copy this rather than you can reference it, right? So you'll be able to edit it. Another way, I won't recommend to copy this and change it, but rather I would recommend that you just add as a reference and then create a local copy of the substrate. Okay, and then you have a summary, and that's how you make a workspace. So let's go ahead and make a workspace. Let me see if I'm recording. Okay, so let's make a workspace in ADS. So this is going to be the start of chapter 1. Okay. Okay, so when you launch ADS, there are two ways or three ways of launching. Okay, one is, sorry. So one is, so this is a parent window. This is called the main window, and this is getting started is a child window. So basically when child is open, it won't allow you to do other things. But let me show you. So you should be able to start ADS from this menu, a start menu for Windows, which is over here, or there would be a what do you call, over here there would be a shortcut for that, right? So you will be able to use shortcut. So once you launch it, the first window which comes up is this one, and this is now simplified as compared to what I showed you earlier. Okay, in earlier versions this window has gone through changes, right? So let's show you. Okay, okay, so basically, bear with me, this window, okay, this is getting started window. So you see over here you have workspaces, and then you have resources for e-learning, and then videos, online videos and stuff like that, right? So now that has been simplified, right? And what you have is just a window like this where you have a recent workspaces over here, and then you have got some commands over here where you can unarchive an example project, you can open an example project, you can open a workspace which is already existing, or you can create a new workspace. So I will create a new workspace here. So as soon as I do that, I will call this as chapter 1 in ADS, right? So this is chapter 1 in ADS. Now it says set up layout technology immediately after creating the library. So this is to do with the resolution. So if you remember in the presentation I showed you, there is a dialog box which allows you to set the layout resolution. So as soon as you create a workspace, this window will pop up and say, okay, what is the resolution, stuff like that, right? So what you have to do is you can look at more details, and here there are two options here. One is compatible with ADS only, other is compatible with IC tools. So basically these process design kits are available in two flavors. One is the native flavor, which is basically PDK explicitly done for ADS, uh, and then there is something called GPDKs, okay, general PDKs, or they are called IPDKs or interoperable PDKs, right? So these would have a different UI, so that you have to click if you are using a GPDK. It's just going to change how the things are displayed onto the schematic and stuff like that. Okay, so now if you want to attach a library, so if you go to change libraries, so there are going to be two libraries which are inbuilt, which are analog and DSP, which are selected by default. Now let's say if I want to do some RFIC or MMIC design, I can use a demo kit provided by them. I can use third-party libraries which are available over here. I can say, so this is the library which I have done myself. It's a study PDK, and it has it doesn't allow you to do layouts, but then it is very good for initial simulations. Then I also have something like from Win Semiconductors, which is a gallium arsenide pHEMT process. You can browse to a PDK by clicking on this link, and then you can go to your default folder and you can look for your PDK. So let's say there's a Win PDK, then this one is your Cree, right? So then there will be something from IHP2, right? So there are different foundries which you have to sign up with, and then you'll have access to these PDKs. And my PDKs doesn't require any signing up. But anyways, so you can attach the library file. So let me show you how to attach. I go to the folder and say lib.dev. So I have to double click on this, or say click on this and say open, right? So if I click on this and say open, then this will appear here. So I'm attaching two libraries, so it will allow you to do multiple fabs, right? So for example, if you want to do entire system, your CMOS design transceiver may be there, then you may have a RF front end which is a gallium arsenide, so you'll be able to do a multiple PDKs. The only thing is that you do not put these on the global or the top level schematic. You enclose this in their sub circuits, or lower level of hierarchy. But let's say I am going to just attach Win PDK and the study one. Okay, so I am going to say okay, and now it is going to ask me what resolution. So if I go to create workspace, okay, so this is the different the different substrate thinning, right? So I'm going to do 2 mil substrate. So yeah, here it comes up. Okay, so now here I'm going to choose this Win, because study PDK doesn't have any layout counterpart, right? So usually I used this grid 0.001 micron, but here it is 0.001 micron Win. I'm going to say finish. Okay, so you can dismiss this. So don't worry about, this is a study PDK, so there are already uh, components in that PDK which are available over here, and you can have a look at them, right? So I'm going to just make a new folder. So it's good to, so this is a folder view for your workspace. This is your library view, and then this one is going to be the file view, right? So here in folder view, I'm going to have this tree, workspace tree, and I want to keep everything well organized in this tree, so I can organize them in folders. So here I can say that these are going to be lib files or library files, so that by mistake I do not edit them. Now this is open library. What it means is that you should be able to see inside the library, right? While in other PDKs you will not be able to look inside the library, right? So we will come to it later on. Okay, so here we have created a workspace, right? Now the next thing is the concept of cells, right? So like in Cadence, every design would be called a cell, and a cell would have a view. So by default a cell should have at least one view, right? So the view can be let's say schematic, or the view can be a layout, or the view can be a symbol. So there are three views which are allowed here, and you can create cells in different folders. So let's say I make a new folder and call it as getting started. Getting started, right? So here in this folder, I'm going to do everything with getting started. So I'm going to make a new schematic, symbol, layout, and there are other things over here which usually people don't use, but as the need arises, we are going to use these. Okay, so I'm going to create a new cell with a default view as a schematic, and this is going to be something which I'll call as, let's say, ideal LPF. Okay, so this is a ideal low pass filter. Okay, and so this is the name of the schematic, and then I would say create schematic. Okay, you can make a blank schematic. You can run a schematic wizard which allows you to use a temp, wizard to establish, or you can use the available templates, right? So there are different templates are available, but here I'm going to start with a blank. Okay, and say create schematic. So once you do that, the schematic window will open. Okay, so let's go back to the presentation and reach to this schematic window. Then I'm going to tell you what is what. Okay, so going back to this presentation. Okay, and slideshow from current. Okay, so this is the main window. This is the main window in for ADS, and we created already a workspace using a wizard. We attached the libraries. We established the resolution for layout, and we didn't copy it. And this is the summary. So we have done this part. Now let's jump into designs. Okay, cells and views. So every design would be called a cell, and cell would have one or more view. You have to have at least one view. Okay, so cell is a functional unit representing certain transfer function. Okay, cell have views. So these views can be schematic, layout, symbol. Okay, so this is the main window. You can click on one of these buttons to open either a schematic as a default view, or a layout as a default view, or a symbol as a default view. You can also use open a data display window which is blank, not associated with any of the designs, right? You can do that. So this is what you can do over here. Okay, so as soon as you click one of them, it tells you what is the cell and what is the view. Okay, enable wizard. So basically in new version it is slightly different, which I have just shown you. Click OK, and once you click OK, you have a schematic which is created. You can also do a layout view as a default view, and that will be created and highlighted in the workspace tree. Notice that by looking at the icon, you can tell whether it is a schematic or whether it's a layout, right? Okay, so schematic window has got a menu bar which has file, edit, select, view, insert, options, tools, layouts, simulate, and most important of them is going to be edit, select, and options, tools, layout, simulate. So these are the most important ones. Okay, so then there is another another entry in this menu which is called dynamic link. So what is dynamic link? Basically you could have a schematic in Cadence. You can netlist it in Cadence, bring the netlist to ADS. So both of them have to be on the same machine, on the same OS. For example, Cadence runs in Linux, then the ADS which you have to run is a Linux copy of it. So you'll be able to run ADS along with Cadence. Now ADS is going to do the simulation, optimization, and stuff like that on that netlist, right? So that is the dynamic link. Then design guides are available for to assist you in various designs, but then this is good for study, not for practical implementation, right? So people cannot, people who have first time used it say that, okay, I want to now take it to the physical design, which is going to be a lot different from what you did for analysis, right? So that's the difference you should know. Then there may be some synthesis tools like filter synthesis, right, which will allow you to synthesize a filter. So those are design guides. Then there is going to be a toolbar here in which there are different commonly used buttons. So here one thing which you have to understand is once you initiate a command in ADS by clicking on any button or a menu option, then that is going to repeat. So for example, if you place a component, then you can place multiple copies of the multiple components you can place by just keep on clicking onto schematic unless you press a escape. So if you press a escape or you click this terminate command button, right, so the same command is going to be issued again and again. So that one of your hand has to be on the escape key all the time. So you issue a command, you do something, and then you escape. So you issue a new command and stuff like that. Now this is another very important portion, which is going to be copy and move, right? So if you can select multiple components and move them, you can make a copy of that component, right? So we are going to use this a lot. This is for deleting a component. This is for saving, open, new, and stuff like that, and you can print. Okay, this is for undo and redo. You can do multiple undos and redos. Then this is for zooming into the design, but the easiest and fastest way of design is the mouse wheel. So if you point to anywhere on the schematic or layout and then use a wheel, you can zoom in. Mouse wheel, you can zoom in and zoom out. So that's you don't have to use these. Then you can also maximize to the entire extent of the design. You can maximize a certain portion of the design, and then you can basically zoom in and zoom out. So that's what that is. Here you can go down in hierarchy, right, and here you can come up in hierarchy. So if you have a hierarchical design, you can go down and up. So this we will use a lot. Then you are going to use this button to rotate. So earlier, once you have placed the component on schematic, then only you could rotate. But here, if you have selected a component and it is basically stuck to your mouse cursor, then you will be able to rotate it there itself by clicking this button, right? Then here you can mirror X and Y. Here you can disable the component with either a short or open circuit. Okay, then there are other toolbar items, and these are going to be, you can select a palette. A palette basically means it's a like a library whose components have been uh, grouped together as palettes. So basically, if you have lump components, then all the lump components will appear. If you have microstrip components, then all microstrip components will appear. So this is referred to as palette here. So if you see lump components, if you drop down, you will have all the categories available. What you call all the palettes are available, right? And once you choose a palette, you have all the components in that palette on the left hand side, right? Okay, then you can have a history of components which you have already placed onto schematic. You can add a pin, you can add a ground, you can add a variable to the schematic, you can add a name to the node, you can add a wire, you can do a launch optimization cockpit using this. You can do circuit optimization. Here you can do tuning. So I'll tell you the difference between optimization and tuning. So here you can do circuit tuning. Here you can run the simulations, and this one is if you have multiple schematics, okay, for a same cell, then you can choose which schematic you want to use, right? And this is usually what happens is if you have multiple implementations of same circuit and you are analyzing system, then you have certain policies which you can launch, so which automatically selects which schematic you want to use, right? So this is for optimizing the system performance, and hardly people use it or talk about it, but we are going to do that. Okay, then at the bottom you will see your mouse cursor location, right? And then you see default units are in inch, right? Stuff like that. Okay, and this is the canvas on which you are going to place components. So this is basically your schematic. Okay, so I am going to just show you how do you do that. You can select a palette. You can also put library components. So this is what I was talking about. These library components were available, right? You can place them onto schematic. So we can create a schematic. So now you have a good idea of what is a schematic, right? So let's do hands-on with that. Okay, so with a hands-on, okay, let's do this. So this is the canvas, and you see this is a palette, and this palette says win components over here, right? So we will use a PDK later on. Okay, for now in chapter 1 we are going to just use LUM components, right? So we are going to use LUM components, and this is your menu bar, and you have this dynamic link and everything. So you see that was 2011, this is 2020. Not much has changed, isn't it? Everything almost looks the same, right? So it's just they are organized, and there may be a context-based toolbar. For example, here you see a toolbar from Win Semiconductor, right? So this, you may see that you can drag them. Okay, you can drag them around with this handle, and you can place them or arrange them like this, right? And if you do not see a certain component, then you can go to view, and then you can go to docking windows, say component palette. Now here you can also have a layer window if you are onto a layout, so you can add components, or you can also change the components in two bar like this. You have basic editing, so basically you see that basic editing toolbar is over here. So all this is basic. Then you have got these, so mirror and all that. If it doesn't show up, just right click and say basic editing, right? And then you have DC annotation. So here basically it just says if it's not visible, you can make it visible. So it's now available here, so you can annotate voltages and currents here. Okay, then let's see what you have. High speed design you don't need. Insert instance components. Okay, so this is your PDK context library, which you can disable, so you have more space here because you're not going to use that. Okay, select, deselect. So I don't need select, deselect. Okay, simulation. So basically that's that. So that's basically tuning, simulation, optimization, and then selecting the one of the designs. Okay, and then you have got zoom in and zoom out, which is basically over here. This is zoom in, zoom out. So this is a schematic. Now to place a component, for example, okay, let's see what is followed in this schematic capture. So you can place the components. Okay, so let's do this slideshow. Okay, so here working with components are available from categories in built-in libraries, like these are called palettes. So you can use a drop down menu to choose a certain palette. Once you have chosen a palette, it will show up like buttons on the left hand side, right? Then what you can do is you can place components from these. So this is a resistor, for example. So components are going to have these pins, while the models, if you see here, don't have pins. So one mistake a beginner does is try to use a model in a circuit schematic, which will not connect because there are no pins to it. So this is a model for a component which is on the left hand side. Okay, so you can place various components. Now the pin changes color as soon as you connect it. So if you connect it with wire, you see the red the red changes to blue. Okay, so that means that that node is connected. Okay, and then if you want to move a text, you can press function 5 F5 key, and then you'll be able to move the text. So you select a component, press F5, and you'll be able to move the components. Okay, then there is something called on-screen editing. So what is on-screen editing? You will be able to edit the value of various components on screen itself. You can just type it in here like this, change its value, right? So I can make a circuit for circuit simulation. So now a simulation means you should have a valid circuit. What a valid circuit is, it should have supply rails. It should have the circuit which is connected properly. There are no disconnects in the nodes, right, and stuff like that. And then you have got terminating or terminations you have. So first thing what you need is a circuit which is well connected. Second thing you need is sources and terminations. So terminations also means source and sinks. Like for example, source is your VDD and sink is your ground. So you should have a circuit with VDD and ground. Sometimes people forget to place a ground and then they don't get the good results or the results they are expecting because there is no ground, right? The circuit has to operate between two supply rails, VDD ground or VDD or another negative supply. So that is there. And then the third thing which is there is terminations. Like for example, if you are working with microwave circuits, then the inputs and outputs have to be terminated in certain impedance, like a 50 ohm impedance. So there is a term component which you have to use for termination. So once you have a circuit and source and sink and termination, then you should have a simulation controller. So this concept is very simple to understand. Each schematic can support multiple controllers, but then the results are going to be nested, right? So you should be able to parse the result out of it. So it is recommended to use only one controller on a schematic. Now if you want to do another analysis, just make a copy of that schematic and change the controller, right? So that's the way to do it. Like unlike like Genesys or unlike Cadence, where your simulation is a separate unit, and then your schematic is a separate unit. It's not like that in ADS. In ADS, a schematic has a simulation controller which tells what kind of simulation you want to perform. So simulation controller. So these three things are must: circuit, terminations, and controller. Once you have that, you have the proper circuit which can be simulated. So to create a schematic, we have seen how do you create this. You create a schematic. So now this is going to be slightly different with the older version. Okay, so we create a circuit like this from the lump components, and you can place them, and then you can use the wires. You can also rotate components using that button, right? And you will have a circuit for simulations. Okay, now the sources. Okay, now let's say if I'm doing linear analysis, then there are only 50 ohm terminations. But otherwise, if let's say we are going to do harmonic balance or let's say a transient, we might have to put sources, and these sources may be pulses, it may be a sinusoidal input, it may be a power input, or it may be a voltage waveform, it may be a current input, right? So these sources can be frequency domain sources. So they are used for frequency domain simulations, but it's not that they will not be used in time domain simulation, but it's just that it's better to use frequency domain sources with frequency domain simulations. Then there are time domain sources. Then there are modulated sources. So for example, if you want to put in a source which is a source of let's say Wi-Fi signal, so you should be able to use modulated sources. Then there are other sources which are like control sources, which are basically used for modeling. So you'll be able to put in noise source. You can put a source which comes from another bench in Ptolemy, like a DSP signal, right? So you'll be able to do DSP based sources. Okay, so here I'm showing you linear or S parameter simulation. So if you don't know what are S parameters, please go ahead to another playlist on microwave and millimeter wave circuit design. There I talk about what are S parameters and stuff like that, or scattering parameters. Now when you do S parameter analysis, you have to do termination into a impedance, a system impedance, like 50 ohm. So there are terminals like this, so which you can place around the circuit. Now this is a well-formed circuit because it is a passive circuit, doesn't need supplies, right? It doesn't need VDD and ground, so it needs ground but not VDD. Then it has proper termination. So this is a schematic which qualifies for simulation, right? So then you can place a simulation controller. In this case, I'm going S parameter simulation, so I'll put a S parameter simulation controller. Okay, so that's the controller. Usually the first button is a controller in the simulator palette, simulation palette. So it's simulation S parameter. So first button is S parameter controller, and here you can specify the frequency range for which you're going to do the simulation. So if you double click it, another dialog box will open which will allow you to set this, or you can do a on-screen editing. Okay, you can set the start and the stop points, and then the step size and or the number of points, right? So it will take either of them, and you are ready for the simulations. So I'm going to create the same schematic so that we just follow this, right? So let's do a schematic. So we have a blank schematic. So I have an inductor here which I place here, and then I have a capacitor which I can select, and then if I want to rotate it, I have a rotation button here. So I will place one over here, other over here, and then I have got ground here. So this is ground, and then I can connect the wires in between. Okay, and then I'll be able to go to another palette which says simulation as parameters. Here I will find the terminations. So this is port 1 and this is port 2, and then they will also have ground. Okay, so now if the text comes in between, like here, it's kind of messed up. So I can do one thing is, every time if I want to end it, I have to press escape, right? Select the company and then press F5 is taken here. Okay, so okay, I'm going to move it through that because F5, I have configured F5 for my recording purposes. Okay, it's going to terminate the recording, so I'm going to move text. Okay, so now the texts are done. So now I can use the scroll wheel of the mouse. So wherever I point, I can zoom in there and then zoom out, right? And if I place it on one of these, then I can pan it, one of the sliders, right? If I place on the vertical slider, I'll be able to pan it. So this is my schematic, and then I need a simulation controller. Okay, here I can put in a value. Let's say I want to go from DC to 10 gigahertz instead of, let's say, megahertz, 10 megahertz. So I can do on-screen editing like this, or I could have done editing here by double clicking it, and then I'll be able to change these values, correct? So this is my linear sweep. I can also use a logarithmic sweep, and I can also do a single point, right? So I can do a center and span also here. Then I can also use a sweep plan. So I have to specify a sweep plan where I can choose discrete frequencies or disconnected ranges. So that is called use a sweep plan. For now, I'm just going to do a linear sweep of frequencies and click OK. So I can save it using the save button, and then I can hit this button which says simulate. I can hit simulate and it will simulate the results. So I'm going to use get the S parameter matrix.
Okay, so this is a simulation status window. It highlights any warnings and stuff like that. So there are nothing. It completed it and then it opened a data display window, which will happen to have the same name as the schematic. And it will also have the same data set as the name of the schematic, right? So now later I'll show you how to do multiple data sets. Now here I can put a rectangular window, right? So there are different windows available, various graphs which are available. I can plot it on a rectangular plot. I can plot the things on Smith chart. I can plot the things on polar chart. Then I can have the rectangular chart which is split up into multiple subplots, right? Then I can put a table here. Here I can put antenna patterns, right? So these are mostly polar plots which show you gain, directivity, and stuff like that. Here I can write some equations. Here I can draw lines, a polygon, a polyline. I can draw a rectangle. I can draw a circle. I can add a text. So all I need to do here is put a rectangular plot. As soon as I place it, it comes up with this dialog box, and I can choose what I want to plot. So let's say S21. If I do add, it will just add the plot. But now here it's a complex data, so I can look at the in dB, or I can look at the phase, right? So let's say if I want to look at the magnitude, I can look at the magnitude in dB. So this is what my graph is. I can double click on this and I can change the properties of a graph. I can make them thicker. I can make them dotted. So if I want, I can make them dotted, or a short dash, for example, stuff like that, right? So I can do that. I can also access that from double clicking the graph and then clicking on the plot. And here I can also change it to, let's say, trace type. I can change it to these. So in this case it will be arrows, so lots of arrows in here, so I'm not going to do that. So I can go to trace type. I'm going to choose the connected trace type, or I can put auto, and we are back to where we were. And I want a solid trace, so I don't want this dotted, so I want a solid line. Okay, apart from that, okay, at the data points, so what are the data points? 10 megahertz. So let's make this, for ease, let's make it 100 megahertz. So once you do 100 megahertz, it's not going to be as smooth as 10 megahertz step, right? So if I do a simulation, so it's there. Now I can do one thing. I can place a symbol. So the symbol can be a circle. So now at every data point there is a circle. So let's say if I want to do this as, instead of 100 megahertz, let's say 500 megahertz. Okay, so now you see that these are my points, and then there is a trace in between, right? Okay, so I'll be able to add these circles. Okay, I can also put here stars, so I can change them to stars, right? So all this I can do here, okay, or no symbol. Okay, and another thing is auto space. Let's say I want to do circles and auto space them out. So it will automatically decide, whether to put for all the samples or whether to put for different samples. So let's say if I go back to, let's say, 10, let's see how it picks up the sample. Okay, so it didn't do that. It has automatically chosen certain number of samples to put the circles. Okay, so now here you can also display label. So basically here there's nothing on the display label side, but when you do multiple, like when you do sweeps, you will be doing this display label, right? So for example, I can do another sweep where I can sweep this inductor value, right? So to sweep this inductor value, let's add a variable called ls, right? So this ls variable is 1 900, so I have to declare a variable first. So I will call this variable as ls. and this is a default value of 1, but then I can sweep it. So I go to parameter sweep. So one of the sweep is the frequency sweep, or one sweep is allowed in the controller. For another sweep, I have to put something called parameter sweep. So here I can sweep ls, and I can go from zero point 0.5 to 1.5 in steps of zero point 0.5. So there will be like three different traces now. Sorry. So now S21 will be three different traces. Okay, so we have done that. Now here, if you are sweeping one of the variables, then it has to show. So this is like a for loop, right? So for zero point 0.5, simulate all the frequencies. Then for 1, simulate all the frequencies. Then for 1.5, so it is going to do the S parameter simulation 3 times. So it is sweeping frequency in the controller, but then it is sweeping ls. Now these two for loops are not related to each other, right? So we have to tell the simulator which one is the inner loop. So the outer loop always points to the one loop which is inner. So for example, here I can double click it and go under simulation and say my inner loop is under DC control, DC1. So this is called not DC, sorry, SP1. SP1. So the inner controller is SP1. Okay, so it shows up here. So I have an outer loop and an inner loop. So now if I hit simulate again, so now there are three curves you can see. Okay, one curve is for ls equal to 0.5, other curve is for ls equal to 1, other curve is for ls equal to 1.5. So this is what that label does. So if I have a display label, if I don't have display label, then it will not show which one is what. Okay, unless you bring your cursor on it, then it will show you that this is for ls equal to 0.5. So if it's good if you put label in here. Okay, so you'll be able to do that. So this is how a simulation is done, and then I've shown you how to sweep a variable, right? Now let's go back to not sweeping the variable. So I'll just do an undo. Okay, so I am not sweeping the variable here. Instead, sorry about that. Instead, I want to change a component value. Let's say I want to change this component value, right? So instead of simulation, I will put in tune. So what tune will do is it will just netlist it, and then it will declare these as variables. Now I can pick up any variable. So for example, if I hit tune here, okay, so this tune parameter window appears here, and I can choose any component value. Sorry about that. Let's say inductor. So that inductor available as a tune. Now I can also put in here this capacitor and this capacitor. So I have three values which I'm going to tune. So now these are inserted in the netlist as variables, and the control for those variables is available from here. So if I display the display window here, and if I move one of them, so you see how the inductor affects the performance. You can see that, right? Or how this capacitor affects the performance. Okay, now there are two capacitors, so both capacitors are acting independently. Now you may decide that I want to move two capacitors together, right? In that case, I'll just close it and say, do you want to save the tuned parameters back onto Schematic? And say no. Okay, so instead of doing this tune, I can put here, so I can remove tune by just deleting this, and here I can declare this as CS. Okay, so this is CS in picofarad. Similarly here, I can remove this, delete, and I can put here CS in PF, picofarad. PF picofarad. Now, if I use a variable onto schematic, I have to declare that variable. Like in C, if you want to use integer, let's say integer or a float, okay, which is A, then you have to basically declare it before you can use it. So in my case, that variable is CS. Okay, default value is let's say 1. Now I can change it, right? So now why did I do that? I can hit the tune button, and I know my inductor is can be tuned, but then I can change the capacitor value. Now both capacitors are going to change simultaneously because I have declared them as a variable, and then I'm tuning the variable. So if I go to schematic to display window, then I can change both of the capacitors together, you see, and you can see the effect. Now one more thing you can do here is right click on this and say add the history mode. So what history does is that it saves the previous state. For example, if I change this value to, let's say, 1.2, right, and click anywhere, so you see the history basically says that, okay, you were here, and now that you have changed the inductor, you are here. So if I change another value, let's say zero point 0.6, right, click somewhere, so that's that. So the original one is there in red, then you have the another one, so now it will do three of them. So if I change this to 0.9 and click again, so that's what's happening. So if I keep changing it, so you can see that there is a history on it which tells you what is the trend. So history basically tells you the trend, it doesn't tell you anything else. Okay, so this history is telling you the trend. Okay, now you can turn off the history. Okay, now you can see each one separately. Now if you like certain tune, for example, I like something like this, then I can go here and store it, and I can give this as, okay, uh, optim1. So this is my best result, and say okay. Now I can keep tuning it. So there is a dotted line which says that this is something which you have already stored, so I will make it bigger. So this is already what you have stored, and if you keep tuning it again, right, and let's say you like this, you don't like this, for example, then you can say recall optim1. So you are back to all the same component values you see here. So let's see if I change this and I didn't like this, so I can say recall to memory1 optim1. So it has placed back CS to 1.37 and the trace back to where it was. So once you are done with the tuning, you can say update schematic. So when you hit update schematic, these values got updated. Okay, and then you can hit close and say yes. So basically now you have tuned. So this T basically shows that this is tuned in this range by this step size. Okay, so this is about tune. Okay, now let's look at one more stuff before we end it, right? So let's say I want to post process the result. Okay, so this is S21. Let's put here other parameters, S11, again the magnitude, and I can put this on the right hand axis. So I can choose the right hand axis. So this goes to the right hand side axis, right? So this is your S11, and this is going to be symmetric. So I will have S22. I can double click it, add S22 dB. So that's S22, which I can put green color so that it is visible easily, right? And S22 basically has to be done on the right hand side. So S22 I can go to plot axis and right hand side axis. Okay, so they are overlapping. So this is a symmetric circuit. So now what I want to do is I want to tune them such that my S parameter in this frequency range up to 6 gigahertz is less than 10, minus 10. Okay, so this I can do one way. Either I can play with the tune or I can let it do it. So to be able to let it do it, I should be able to launch from here. So I'm going to first remove the tune from here. So I can just say delete. Okay, by the way, you can disable by putting a minus T here also. Right. So I'm just going to delete this. Okay. So now these values are fixed. Now I can say I want to optimize it. So I will launch a optimizer. Now this is what I will recommend is the says unable to obtain component in the design. Of course, you have to put goals and all, right? So what you have to do is you need to go to OptimStat. Where is that? Yeah, here. Okay. Here you have to put here a controller. Okay. So now what is this controller telling me? This controller telling me that I want to do a random optimization. I want to do a gradient optimization. I want to do a random min max, gradient min max, quasi Newton, stuff like that, right? So it is telling me a lot of stuff here in terms of optimization, right? Then there are goals here. So right now I am saying use all the goals. I haven't specified any goals. Here the number of iterations, let's say, is 50 or 25. Okay. Then here is desired error. So if you go to advanced, then you can also change the relative tolerance and stuff like that. And you can say that if there is a variation of so much, then only proceed. If it is not varying, then stop. So stopping criteria is there. Okay. So let's do some goals. So I am going to put here a goal. Okay. So a goal is available from here. It says goal. And here I have a goal on S11. Okay. So analysis is SP1 and the goal here is DB. Okay. S1 comma 1. So you will have to type it. Sorry. So this is your S11. Okay. And the goal is I can put a frequency limit. So I want to optimize this up to 6 gigahertz, right? So I can say frequency range. Okay. So I can go from DC or 0. I think I can put units 0 gigahertz to, let's say, 6 base gigahertz. So this optimization from 0 to 6 gigahertz, and I want this to be minimum maximum value. So I want to put a maximum value on it. Okay, so the maximum value is minus 10, right? So right now there's a goal like this, and say okay. So what has happened here? Typing mistake. And say okay. Okay, so now I have a goal here. Now in optimization, I can choose a specific goal. Okay, so this is called Optim Goal 1. So I can name it. So for example, here I can say IPRL, IPRL, input return loss, right? So if I go here, that IPRL is available here. That's the only goal available. You can selectively add the goals or you can add all the goals. Okay, so I have set the goal and this is the weightage. So when you do multiple goals, I can put the weightage for each goal, okay, which will help in computing the error function. Okay, so I'm going to do a random or a gradient. So let's do a random first. Okay. So once you are done with this, I have to click this optimize. So you have to have a optimization controller here, and you have to have at least a goal here to be able to run this optimization. So it will launch. Okay, so now I also have to say what am I going to optimize. I'm going to optimize this guy, right? So here I can double click on it and I can go on tune optimstat, go under optimization and then enable it and then provide it a range. Or I can do it from one shot from here uh, using simulation variable setup. Okay, so here I want to optimize L, and this is the min max value I can provide here. Okay, so 0.422 1.26. Okay, then I can optimize this component value, right? So I have done, so this is for tuning, so I'm wrong here. So you should go to variable setup. So don't do under tuning, do under optimization, this and this. Okay, and say when you say okay, O will appear. So if you click on, so let me put a escape here. Okay, if you click on one of them, so just like tune, it says opt. So in this range, it has to optimize. So let's launch this again. So this is called optimization cockpit, and this is computing my error. For this range, I have to be less than -10. Okay, so it tried its best, and it tried to get it below -10. How about -15? So I can update the goal here. I can set this to -15, right? Say okay, and I will run this again. Continue. So it has optimized it to -10. So it is not able to adjust this, right? So you can click here. So this has to be reduced. So it has hit the boundaries, right? So I can do this. I can say update design and say close. Then I can go back and check where I'm running out. So 0.688. So I can lower this. I can lower this to, let's say, 0.4. Sorry. Point. And dismiss this error. And I can lower this one. So this is hitting the upper limit. So I can make this as like 7. Okay. So now I have more space to optimize. So I launch the controller again. So it is going to do that. And now it has come below 15. You see here? It's come -18, right? So this is done. So it allows you to also, intervene in this optimization by doing start tuning. So here, the same tuner is available here. I'll tune it here, and then I can say update design. Or I can edit goals here, edit algorithm. So I can change this algorithm from random to, let's say, gradient, min max, and all that. I can also change the number of iterations and click OK. So I can edit the algorithm from here. The goal I can adjust from here. I can do my own manual tuning over here. And once I'm done all with this, I can do a store and then recall, just like in tuning window. Or I can revert back to the original condition where I started from, right? And then I can also say update design and say okay, and then close it. Okay. Continue simulation, keep the optimization of cockpit, close optimization cockpit. Okay, so now if I hit this, I have a result which is better than 15. Now, is this a good way of designing? Answer is no. Okay, the good way of designing would be if you can compute these values. So you design a filter using pen and paper rather than depending on an optimizer. Though optimizer can do a lot of things, but it doesn't give you any insight into what it should be. So now we have looked at tuning, optimization, and simulation. We have also looked at the visualization, right? And in a rectangular plot, we can also plot S11 in the Smith chart. So that's what S11 looks like. And then we can also plot as true on a Smith chart like that. It's symmetric. And so this is my design. Okay, so here I'm going to stop for chapter 1, right? And I'm going to go to chapter 2 in the next session, right? Okay.